Hello class, welcome to exercise 1L, further applications of simultaneous equations. While we've had a look at some applications in the questions attached to the previous lessons, in this lesson we focus purely on applying the skills we've learned in the last two lessons. So our first example is example 31, setting up and solving simultaneous equations. And your pre-learning for this example will be questions 1 and 2 for the new book and questions 3 for the old book. And then we'll do example 32, which is solving further applications with two variables. And the pre-learning for you to complete with this example is questions 3 in the new book and questions 5 in the old book. Okay, and I'll see you in the introduction. So far we've learnt how to solve simultaneous equations using the substitution method and the elimination method. Knowing how to solve simultaneous equations is well and good, but it is their application that is an extremely important tool in real-world problems and general number problems too. For those of you who want to be maths teachers one day, I'll just let you know that we use these techniques all the time to find particular numbers for certain questions. Because we've covered most of the skills in previous lessons, we can move quickly to these examples. But some points you're going to need to take down before you use simultaneous equations for applications are: first, we'll need to decide what our two variables or unknowns are. Then we'll need to write down two linear relations that describe the worded problem. I should also mention that so far we've used x and y as the variables and unknowns. However, when working with such practical applications, it often makes more sense to use a letter that makes it clear to us which variable is which. So once we have our variables and our linear relations, then we need to either use the elimination or substitution method to solve the equation. And finally, we write the solution in words. Also note that we must have two linear relations that aren't parallel lines to solve for two unknowns. In BCE, you'll learn that you can solve linear relations with three variables with three equations that aren't in a 3D classification of parallel. While that's not your concern now, I just mentioned it to make it clear how important this topic is. Okay, let's move on to the next section. Okay, so this section is about setting up and solving simultaneous equations. There's not a lot to add other than what I've said in the introduction, but let's state it one more time. When we're given a worded problem, we need to search through there to find the two variables or unknowns and the two statements that end up being the linear relationships. Let's move straight to example 31, where the question is, the sum of the ages of two children is 17, and the difference in their ages is 5. If Cara is the older sister of Ben, then determine their ages. So the unknowns in this case are Cara's age, which we'll denote as K, and Ben's age, which we'll denote as B. So to say that their ages sum to 17, that means Cara's age plus Ben's age equals 17. So using the pronumerals we have here, that means K plus B equals 17, which I'll call equation 1. Now, because the difference between their ages is 5 means that if I subtract the smaller age from the bigger age, we'll get the answer 5. And it states that Cara is older. So we'll write this out as Cara's age minus Ben's age equals 5. So once again, using our pronumerals, that's K minus B equals 5, which we'll denote as 2. So looking at our two equations, we can see that all pronumerals have a coefficient of 1. Both K's are positive, so I'd subtract one equation from the other to get rid of K, or one of the B's is positive, the other is negative, so if I add them together, that eliminates B. So let's add them together first. Equation 1 plus equation 2 will be 2K plus 0B, so we can ignore that, equals 17 plus 5 is 22, which is the same as saying K is 11. And if I was to sub K equals 11 back into equation 1, we would get 11 plus B equals 17. And subtracting 11 from both sides means that B is 6. And because we give worded answers to worded questions, this means that Cara is 11 years old and Ben is 6 years old. And we can test out what would happen if we go the other way. So let's just subtract equation 2 from equation 1. That would mean that we get K minus K, so that eliminates K. And we get B minus B, which is the same as saying 2B, is equal to 17 minus 5 is 12. So in other words, B is equal to 6. And there's no need to go any further because you can see I have the same result. All right, I'm just going to close that off, but also please notice the wording in the answer here. This is the correct method to answer a worded question, okay? I've already stated that a few times, but just make sure worded question, worded answer. So I suggest you pause the video and do the pre-learning for this example, which is questions 1 and 2 if you have the new book, or question 3 if you have the old book. Okay, assuming you've done that question, welcome back. But before we move on to the next section and the example with it, I'm going to set 2 challenges for you. The first one is the one that's called the lesson starter in your text, which we'll do in class. And this one is challenge 1, which is Nathan heard on the news that his football team scored 19 times for a total of 79 points. Considering a team gets 6 points for a goal, 1 point for a behind, how many goals and how many behinds did they score? You can pause the video to jot that down or look it up in your textbook. Typically, for a question like this, the challenging part is to find out what is your pronumerals or your unknowns. Once you've done that, solving the simultaneous equations themselves might not be that tough. But it always is tough to find the maths in the words. All right, let's move on to challenge 2. This one's a little more challenging. So the question is, a mother is 5 times her son's age. In 6 years' time, the mother will be 3 times the age of her son. What is the current age of the mother and her son? Once again, you might need to pause the video to write that down. All right, good luck with those challenges.
I'm lucky, I have algorithms.
It's time we move on to the next section. I'll see you there. Okay, this section is solving further applications with 2 variables. The situation you're going to see in the example for this section is the most common use of simultaneous equations in the real world. So let's get straight into example 32 and we'll talk about how it's so applicable after. So the question is, John buys 3 daffodils and 5 petunias from the nursery and pays $25. Julia buys 4 daffodils and 3 petunias for $26. We need to determine the cost of each type of flower. I'm guessing the colouring makes it obvious, but our unknowns are the cost of each flower. And so we'll denote daffodils as D and petunias as P. So this means John's purchase can be rewritten as 3D plus 5P, which equals $25. And we'll name this relation 1. And Julia's purchase can be rewritten as 4D plus 3P, which will add to $26, and we'll name this relation 2. I'm going to focus on eliminating D, so I need to find the lowest common multiple of 4 and 3, which is 12. So that means if I multiply equation 1 by 4, I'll end up with 12 daffodils, right? Whoops, it looks like I forgot to write 12, which I'll do here. And this equation here, 12D plus 20P equals 100, obviously 4 times 1, we'll rename that as equation 3. Now again, focusing on getting our daffodils to 12, if I multiply 4 by 3, I get 12. So I'm going to multiply all of equation 2 by 3, and that will give me 12D plus 9P equals 78. And we should name this equation 4. Equation 3 and 4 both have a D with a coefficient of 12. So if I subtract 4 from 3, that will eliminate the D, so I can ignore that. 20P minus 9P is 11P. And that'll be equal to 100 minus 78, which is 22. So dividing both sides by 11, that means P is equal to 2. So if I sub the value of P equals 2 back into equation 2, we now get 4D plus 3 times 2 is equal to 26. So obviously 3 times 2 is 6. Subtracting 6 from both sides means 4D is equal to 20. So therefore D equals 5. So therefore the cost of a daffodil is $5 and the cost of a petunia is $2. Okay, so at this stage I suggest you pause the video and have a go at question 3 in the new book and question 5 in the old book. And when you come back, we'll summarise this lesson. Okay, I think you should be able to see why this type of simultaneous equation is so common. In any sort of situation, we could use 2 different volumes of 2 different unknown values and measure the total outcome. Then we could use simultaneous equations to figure out the value of each unknown. The catch to this method, though, is that we need to find 2 linear relations between the 2 unknowns that can't be represented as parallel lines. Finally, you should consider this lesson a success if you understand that it's necessary to form 2 equations when there are 2 unknowns in a worded problem. Know how to define variables and set up equations from word problems. Can choose an appropriate method to solve 2 equations simultaneously. And know how to check an answer and answer the question in words. Okay, well, congratulations on making it to the end of the unit. I will see you in class.